Hi, welcome to Apsana classes. Today in this video, let's learn about the full adder. Before learning about the full adder, let me tell you one word. So continuous improvement is better than delayed perfection, right? So all of us have different works, different tasks to complete on. But it would be better to start little things and make just continuously improving that little thing and to greater work is better than making the whole work with imperfection and the perfection at a time is just not correct to my opinion. So let's see. So everyone have a different opinions. That is my opinion actually. So full adder. So we know that the full adder is a combinational logic circuit. Why? Because it depends upon the output of the full adder depends upon the only present inputs. It doesn't depends upon a past outputs and present inputs combinedly. So that is a sequential logic circuit. We are talking about the combinational logic circuit, which is an example of the full adder. So the design. So to design the combinational logic circuit, we have 6 steps that we have already discussed in our previous class. So step number 1 is analyzation. What is our analyzation here? We have to design a full adder. Okay, fine. Full adder. And then next one, determination of number of inputs and outputs. So how many inputs that a full adder can add? It can add 3 binary inputs and can give 2 outputs for the sum and carry. So 3 binary inputs and 2 output for sum and carry. So step number 3, assigning the names to input and outputs. I am assigning X, Y, Z. You can represent as A, B, C, D, anything. So X, Y, Z for inputs and sum S, and for carry I am giving C. And the next, deriving the truth table. So how to derive the truth table? So truth table based upon the inputs and outputs relations we get the truth table. But here we are having the 3 inputs. So we get 8 combinations. It is based upon a 2 power n. So n is here 3, so that we get 8 combinations. So 8 combinations we get for input. Let me draw the truth table. Truth table for inputs and outputs. Yeah, for inputs X, Y, Z, and outputs sum and carry. Fine. But here the X, Y, Z representation will be done in binary form. That is an 8421 code. That too in 8421 code. So we take only 3 digits and that 4 to 1 is representing from 0 to 7. If you add whole 4 plus 2 plus 1, we get 7. So from 0 to 7, that 4 to 1 code will represent it. So which means 8 combinations. 0 to 7, 8 combinations, right? So what are those? 0, 0, 0. 0, 0, 1, 0, 1, 0. It is nothing but 0, 1, 2. So how it become 2? Because we placed the second positions as 1 and we made every position to 0. So 2 only representing and all the positions are represented with 0. So 2. If you would like to get 3, just represent the 1 to 1. So we get 2 plus 1, 3. So 0, 1, 1 is representing for 3 in 3 bit. If you would like to get in 4 bits, the 3 would be 0, 0, 1, 1. You know, I think so, of course. So 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Yeah. Then what is about the outputs? So as it is adding, we have to add the 8 combinations each by each, 1 by 1. So 0 plus 0 plus 0 is 0. So we get the sum 0 but carry as 0 because if we don't get any carry, we assign the carry simply to 0. So how to give the carry and sum for? Means least significant bit to sum and most significant bit to carry. Okay? 0, 0. Here we get 0 plus 0 plus 1 is 1. So assigning 1 to sum and 0 to carry as we don't get any carry. Same 0, 1. And then here See, 0 plus 1 plus 1. In decimal, we know that 1 plus 1 is equal to 2. But how to represent it in binary? 0, 0, 1, 0. But we are taking only for 2 digits for sum and carry. That is why most significant bit is going to be 1 and it is going to be 0. Okay. Then here 0, 1 and here 1, 0. And 1 plus 1 is 2. So 1, 0. And here 1, 1, 1. In the 7th position, we are having the 1, 1, 1. Means total 3. So how to represent the 3 in binary? 1, 1. So we are giving 1 for least significant bit and 1 for most significant bit, that is a sum and carry 1, 1. Hope you got. Okay. Then we have drawn the truth table. Then next one, Boolean expression we have to get. Why I am telling the simplified Boolean expression? Because I am using the kmaps. Of course, from here you can get the Boolean expression. It should be solved again in order to simplify. So in order to get the direct simplified Boolean expression, after the next step, I am using the kmaps. Of course, kmap too having some rules. Normally, Boolean expression can be solved with the theorems and losses, that is OR and etc. But for direct steps, we are using the kmaps. Let's see what are the rules in a kmaps to represent and to get the Boolean expression. Boolean expression from kmaps. So kmap is nothing but a method to get the Boolean expression in a simple way on using cells. So how many cells that we are going to represent it in? As we are having 3 variables x, y, z, 3 variables we are having. We represent in 8 cells. Why so? It became depends upon 2 power n, that is 2 power 3 is equal to 8. So 8 cells we need to draw. Okay, fine. Of course, you can draw vertically too, but I am drawing horizontally for my easy representation only. So I am taking one variable x here and 2 variables as we are having, so 2 cells are associated to one variable. Each variable is associated with the 2 cells. So x here, y, z. As having only one variable, we take one digit, 0, 1. So as we are having the 2 digits here, we take 2 decimals. 2 binary digits. 0, 0, 0, 1, 1, 0, 1, 1. If you say like this, it's strong. Because in truth table, we have one condition that the representation should be in gray code, which means 1 bit change code. Only 1 bit has to be changed to its adjacent cell. So, but here 0, 0, fine. 0, 1, only 1 bit is changed, that 0 is changed to 1. But here if you see here, 2 bits are changing at a time. But in 1 bit change code, which means gray code, only 1 bit has to change. So that 1, 0. Hope you understood. And then see. So I am drawing for the carry. First I am going to get the Boolean expression in carry. For carry. So for carry, we have ones at which positions? 1, 2, 3. Sorry, 0, 1, 2, third, 4, 5, 6 and 7th positions we are having ones. So how to represent? 0, 1, 2, 3, 4, 5, 6, 7. Why so? Because 0, 0, 0, 0. 0, 0, 1 is 1. 0, 1, 1 is 3. So 0, 1, 0 is 2. Fine. 1, 0, 0 is 4. 1, 0, 1 is 5. And 1, 1 is 7. And 1, 1, 0 is 6. So that is the representation. Nothing here about. And then see here at the 3, 4, 5, 6, 7, sorry, 0. And zeros I have to mention, sorry. 1, 2, 3, 4, 5, 6, and then 7. So at bit number 3, at combination say 3, we have 1, just put 1, and then at 5, and then at 6 and 7. 6 and 7. Then how to group the cells in the kmaps? We have to give grouping also according to 2 power n. So 2 power n means 1, 2, 4, 8 and so on. So 2 grouping is fine. 1 grouping, in order to solve the Boolean expression very simply, so we take groupings in a large way. As long as the grouping is large, that much the Boolean expression will be smaller. Hope you understood. 2, fine. You can draw 2, 2 and then 2. But see, let's see another 1 to 4. Here we cannot group 4. We can group only 3. So maximum grouping is not done here. So we take only 2, 2 and 2. So 3 terms we get. 3 terms. So as I am taking SOP, I am representing in 1. If I am taking in POS, that is in the max terms, I would take in zeros. Okay. So 1, 1 are grouped. Fine. Then how to take the terms in the SOP? So if you consider this grouping, the first grouping number 1, 2 and 3. In a first grouping I have here, so 1, okay fine. So nothing here to cancel. But if you see upwards, we have 0, 1, 1, 1. So what we have common here? In both we have 1 common at the least significant bit. So what are the least significant bit is denoting here? Z is denoting here. So at Z as it is 1. In SOP, if it is representing with 1, you don't need to take with bars. So you can take normally as Z. So first see, X is associated with 1 here. So X here Z plus, and then second grouping. In the second grouping, if you see here X, fine, 1 X. And then if you go up, you will have this in the most significant, you are having 2 ones is a common and you can cancel 1 0. So nullify these 1 0 can nullify, and then 1 1 in common, and that 1 1 is representing here Y. But here Y, you can take directly Y. You don't need to take in bar as it is not associated with bar 0. If it is associated with the 0, you have to take. You must take in bars. Hope you are understanding. So see here, this grouping, third grouping. In the third grouping, we are having 0 1. So 0 1 can be cancelled and just go up here. We are having 2 ones, nothing to cancel here. So we take both YZ as 2 bits are denoting YZ. So YZ. So we got the SOP, simplified Boolean expression for carry. Let's also get for the sum and then draw the Boolean, implement the gates. Implement them in gates. For the same, we have to get the 8 cells X, Y and Z. Means 0 0, 1 0, 1 1, 1 0, 0 1, 0 1. Here we are having the 1 positions at the first and second. 0 1, 2, 3, 4, 5, 6 and then 7. 1 and 2. So 1, 2. Fine. And then at position 4 and at position 7. At position 4 and at position 7. We cannot group 2. We cannot go to maximum grouping 2, 4, 8 because those are individually grouping. So single grouping. We have to give in a single grouping. So for sum, how we get? So see here. First, second, third, fourth. So 4 groupings we get single groupings. So here x simply representing 1. So we get x. But if you see here 0, 0. So 0, 0 is associated with yz. As it is 0, 0, we have to represent it in marks. As it is, we are taking in SOP. In SOP, 0 is associated with the bars and 1 is we can take normally as it is. As we are taking SOP as a min terms. So in min terms, we have to take in this way. Okay. Hope you know all these. Next one, see. Y, z bar plus. So here, if you see here, 0. So as it is 0, we have to take x in bar. X bar. And then here, 0, 1 means y bar z. Y bar z. Then next, here. So 1, 1, 1. No zeros. No need to take any bars. X, y, z simply. X, y, z. The next, fourth grouping. Fourth term. 1, 1, 0. X, y, z bar as we are having 0 here. X, y, z bar. So these two are the simplified Boolean expression that we got from the kmap. Okay. And then the last step, implementation using the logic gates. You can implement these two Boolean expression using universal gates like NAND and NOR, or else in the simple basic logic gates and OR and NOT. So I am using the simple basic logic gates. So here we see. Let me rub out to this. I don't have any work with this. Implementation for sum. In sum we have 4 terms. So 4 terms, and then we have to add all these 4 terms. So we use OR gate. And then we have individually we are having 4 terms. So 4 terms are here with dot product. So these 4, to represent the each term, we have to implement in AND gate. So we have to take 4 AND gates, and then we are having x, y, z. So x, y, z for x, y, z. But for here, if you see here, x bar, y bar, z bar. So we have to give it to NOT gate, which inverts the variable yz. So x fine, NOT gate. If you observe it deeply, it is nothing but the output of a NOT gate, where for the 3 variables. You can also represent the simply sum as this: A XOR B XOR C. Sorry, I am taking x, y, z, right? So x, y, z. So what is the representation then? X, y, z, which gives the output sum. You can directly draw this, but as I am drawing in a basic logic gates, I am telling what is this? XOR gate, right? XOR is nothing but the exclusive OR gate. Exclusive OR gives that. If you have a xy, then x bar y plus y bar x, you will get this, which means like this: xy and then this output. Hope you know all these, but I am saying just for simply. And then x bar, y bar, z. X bar, y bar, and then z. Let me complete here: y, z, y bar, z bar. And then here, how many inversions? No inversions. X, Y, Z. And then one inversion at Z. So Z, Z bar, X, Y. So we have to give all these outputs of AND gates to OR gate in order to add. So we will get the output. So let's see for the XYZ, means for carry. Carry, not for XYZ, for carry. So we are having the three terms, means we have to add, we have to use three AND gates, X, XZ, and then XY, and then YZ. We have to give all those to one OR gate in order to add, and we get the final output this. So we analyze it is a full adder. We given we determine that it is having a 3 inputs and 2 outputs. We assign the names as XYZ and SC. And here determine the truth table I have drawn here with 8 combinations and simplified Boolean expression using the kmaps. I represent the kmaps in 8 cells. Here I have drawn. Hope you remember. And then implementation using the logic gates. So using the basic logic gate I have implemented. If you would like to implement in NAND and OR, please comment me below. I'll surely will make the video. Thank you for watching the video. Please like, share and subscribe.